Hello everyone, thanks for coming. Uh, I am Mehul. I am a data science undergrad, currently working as a research intern at Center for Scientific Computing and Computational Mechanics. And I love applying innovations in machine learning to scientific applications. So if you want to get the access of the slides on your local devices, then please scan this QR code. Okay. So, although physics-informed machine learning is still a fast-developing research area, but this is not a research talk. So, I will focus more on getting a basic intuition of how the physics field of physics-informed machine learning works, its applications, and the Pythonic part, of course, the open source libraries. We may encounter some mathematics, mostly in the form of differential equations. So if you are not comfortable with mathematics, then you don't need to actually worry. I will try to keep the things as much less mathy as possible. Uh, so how many of you started your machine learning journey with Andrew's lectures? Yeah, quite a few people. So a very rough outline. First, I will discuss what are scientific simulations and the challenges associated with them. Then I will focus on a toy example, and through that, I will try to explain the basic working of physics-informed machine learning models, a few applications, and the Python toolbox. And then I will, in last, I will briefly discuss about how can physics-informed machine learning can help in trying to understand the world in a better way. So why do we need to fuse machine learning directly into ML models? Let's try to understand by understanding the differences in usual machine learning applications and scientific simulations. So one of the most common application of machine learning is facial recognition. And in facial recognition, you have access to a huge amount of data, which has diverse faces, and the sample size is mostly usually in millions. And when you train a deep network like a CNN or even a vision transformer, you get a very good performance. But there is a caveat. All these models, this approach of machine learning is quite data hungry. So in regimes where you have data scarcity, these models will fail. So a few scientific simulations. One of the most common application of scientific simulation is simulating the flow of air around an airplane to come up with the most aerodynamic body. Another very important application is simulating the jet flows around the globe, which helps the meteorologists to predict the onset of extreme weather events, which are quite common nowadays due to climate change. Then simulating the dynamics of biomolecules, yet another important application. A lot of progress has been done in this area, and that can be mostly associated to Google DeepMind. And then lastly, suppose an engineer wants to design the most perfect shape for a heat sink to efficiently dissipate the heat from an electronic device. He has to run multiple simulations before coming up with the perfect shape. Okay, so let's design an airplane swing. So when an airplane is in the sky, these are the forces which act upon it. Gravity, which is pulling it down. Lift, which is pushing it in the upward direction. Then thrust, which is due to the constant firing of fuel. And drag, which is just the air resistance. And the wing shape directly controls the amount of lift or drag the airplane experiences. And if we are able to reduce the cruise drag by just 1%, then the aviation company will save around $200,000 in fuel per year. I don't think that is much important, but more important is that it will cut CO2 emissions by 3,000 tons per aircraft annually. So while designing an airplane wing, what engineers usually do is that they employ numerical methods like finite element methods, which are purely based on the physics of the problem and do not make any use of the data which we have. And to explain the process in a very brief manner, engineers build meshes of around 15 to 60 million cells, and on all those individual cells, these complex calculations are being run. And the end result is like this. We get a very nice, very detailed, high resolution simulation of wind velocity around an airplane wing. And this also translates to a very high single design cost. So a single design can take around 10,000 plus core hours, not on a gaming PC, but on an HPC, high performance computer, and also thousands of dollars. So now you can guess why machine learning approach is bound to fail on scientific simulations, because there is a lack of labeled data. It is very expensive to generate data for scientific simulations. Also, in many cases, even though we have some data, it is very noisy. Let's take an example of tracking a cyclone. So while predicting the trajectory of a cyclone, following data is measured through a satellite, cloud top temperature, sea surface temperature, and surface wind speed. And all of this data is bound to be noisy due to the interference of the clouds or just the limitation of the sensors on the satellite. And one more important point is that the usual machine learning models are not made to learn the physics behind the particular system. They are made to learn the patterns in the data, not the actual physics. So they perform very poor on scientific simulations. So how can we infuse physics into machine learning models? We can fuse physics into machine learning models by combining machine learning in the form of neural networks and physics in the form of differential equations, and come up with a very classical architecture in physics for machine learning, which is physics-informed neural networks. So let's try to understand the working of physics-informed neural network through a toy example. And here we will try to predict the trajectory of a ball from ground to ground. In a very ideal world, we have access to huge amount of data, as you can see here. And the data is of high fidelity, which means that it is not noisy, and it exactly captures the trajectory of the ball. And when we try to train a neural network on this data, it exactly fits the actual trajectory. But in real-world scientific simulation, we have something like this. Data is inadequate. It is quite noisy. And when we try to train a neural network on this data, we get a result like this. The model is unable to generalize over the whole trajectory. So let's make our model learn the physics of the problem. So this is a usual deep neural network. X and T, where are the inputs, which are usually temporal and spatial coordinates in the case of scientific simulations, and use the quantity that we are predicting. It can be temperature, it can be position, it can be anything. And in usual machine learning, what we do is that we just calculate the data loss by comparing with the reference data, and we backpropagate it. But in physics-informed neural networks, we calculate the gradient terms of the output with respect to the input using the automatic differentiation feature in PyTorch and TensorFlow. And after calculating those gradient terms, we substitute those gradient terms into differential equation, which is the governing law of the problem which we are solving. And we can put this differential equation as a residual loss and kind of make our model, kind of penalize our model for any deviation from this physical law. Then we combine it with the data loss which we have from the sparse observations which we have, and we backpropagate the loss. So in physics-informed neural networks, the total loss is data loss plus the physics loss. So in PyTorch, this is how we can simply define a physics-informed neural network. First, we define a simple MLP. Then We note down the underlying physics of the problem, which are these two differential equations, one along the x-axis, one along the y-axis. And then we define a function for the data loss, which will calculate the deviation from the available data we have, observation data. And yeah, this is the data. And then this is the important part. We define the physics laws of the problem. For defining the physics laws, we first calculate the gradient terms, which are these. And then we put these gradient terms into the residual equation. And the usual machine learning pipeline, we just train the model. And the results are this. The model, the physics from neural network model, exactly captures the true trajectory of the ball. So one of the most important libraries in physics-informed machine learning is DeepXDE. It is a high-level library for physics-informed neural networks, and it is built upon TensorFlow and Torch backends. And suppose if you have a differential equation like this, you can very simply write it in DeepXDE in a very simple manner instead of all this extra code that you write in PyTorch. So actually, this is the equation of spread of heat on a 2D surface, which looks something like this. And it has various applications, from predicting the spread of heat on a manufacturing material through laser, or predicting the heat spread on a satellite panel. So in DeepXDE, here is how we can simply define the physics-informed neural network. First, we define the geometry, which is the physical boundary within which we want to get our results, get our solution. Then we define the time duration of simulation, and we combine them into a single container. After that, in scientific simulations, most of the observation data is usually in boundary condition or initial condition. So we define a separate container for that as well. And similarly for initial condition. And finally, we combine all of the data we have for our system into a single container, which is, and since our system is evoluting with time, so we have time PDEs container, and in this container, we first define the boundary condition, initial condition data. Then num domain is the number of points on which we want to enforce the physics within the physical geometry, which are just chosen randomly. And num boundary are the number of boundary points which we have, which is the observation data. And num initial is also the observation data, which is just the initial condition. And num test are just the testing points on which we will test our trained model. We define a very simple model like this and compile it, and yeah, it's done. So first we define the geometry, then we define the physics of the problem, the partial differential equation. Then we combine the available data, which is initial condition or boundary condition, put them in a bigger container, choose a network, and then train and compile a model. So a very interesting application of physics-informed machine learning is one-shot super resolution. In super resolution, we try to convert low-resolution images into high-resolution images. Most of it is done using in a supervised manner, where we have access to a high amount of high-resolution data. But in scientific simulation, we do not have access to such high-resolution data. So I want to share this study. So in this study, the researchers had very, very low resolution data of flow of blood through the artery. And as you can see, it is very low resolution. Hardly anything is visible from this data. And researchers wanted something like this, which is a very clear high resolution simulation of blood flow in an artery. So what they did, they first interpolated the original low resolution image. Then they noted down the underlying physics of the blood flow in an artery, which are Navier-Stokes equations. combined it with the sparse data they had, and upon training a very simple 3-layer convolutional neural network, they come up with quite great results. Okay, so if you want to make the best use of physics-informed or machine learning or physics learning models for an industrial or a large-scale application, then NVIDIA Physics Nemo is the go-to library. Again, the benefits, it provides a way more deep abstraction than DeepXDE. Entire training, one more very nice benefit of using this library, that entire training is deployed across a multi-node and multi-GPU infrastructure. So this makes its library very much optimized for industry scale applications. So this library also follows a similar syntax like DeepXDE for prepare. First, we start by preparing the geometry of the problem. And one additional feature is that you no longer have to explicitly define the partial differential equation which govern the system. You can directly import the API for the system. So as you can see here, the underlying equation is diffusion. And we can directly include this in our model by calling the API for that. And rest of the pipeline is same as in DeepXDE. So lastly, what are the big impacts physics-informed machine learning can have on how we analyze the world around us? And one of the applications which really excites me is digital twins. So digital twins are the twins of the physical system, complex physical systems that scientists want to make in order to better understand and simulate the various scenarios that we have involving those systems. And this translates to making a very advanced multi-physics learning model, which can learn multiple physics as well as from the data and come up with a generalizable scientific machine learning model. And through this, we can come up with something like this, which is Earth 2. So I'm not affiliated or endorsed by NVIDIA, but I found this application really interesting. So here they employed multi-physics learning algorithm ForecastNet, which is based on physics learning. And they managed to create a digital twin of the Earth to forecast and experiment the possible scenarios of weather around the world. You can access the repository of the project and the demo from the link. Thank you so much for attending this talk.
Thank you, Mehul. I felt myself in university again, maybe somebody also. So I have a question. Can I have?
Yeah, sure. Yeah.
You have time for questions.
Yeah.
So is it really, okay, what's the connection of NVIDIA technology and the stuff you showed us? Why NVIDIA is de facto only technology here?
This technology, ForecastNet, this underlying model, through this which they made the digital twins, it is open. It is an independent research on neural operators, which is yet another architecture, just like physics-informed neural network. Mm-hmm. But they implemented it using the NVIDIA Physics Nemo library, which I discussed here. So that's the only connection.
So yeah. GPU was crucial to run this model. NVIDIA GPU was crucial to have to run this model.
Yeah.
That's why.
Yeah,
okay.
Yeah. More important thing is the library, which is well optimized for these kind of applications, these kind of models.
Okay, thank you. Some other questions? Oh, please.
Thank you. Very nice talk. I have maybe a controversial comment followed by a question. you are using information from physical systems, but we all know that those physical systems are actually models. I mean, the equations are basically those models. You are presenting here toy models, but when we go to reality, we have something closer to something like an stochastic system, which essentially is, well, first of all, is computationally expensive because we need several iterations to have actually something meaningful. We can have, for example, in this example, we can have MD simulations where in that case, we are only iterating in a partial, only part of the total phase space. And in cases like the one you were showing for finite elements, we are ignoring thermal fluctuations, for example. So in all these cases, we're always going to be biased, is my perception when we have these type of systems. We are trying to run predictions over some sort of approximation. So it's an approximation of an approximation when we do this type of neural networks. Now my question is, how do you reconcile that? Because in the end, you're going to end up with a model that is biased, isn't it?
Yeah. Actually, in physics for machine learning, there is a whole spectrum of such models. So it really depends on the domain. If you have high fidelity data, then you believe more on the data, less on the physics of the problem. And if you are more sure about the physics, that the underlying equations are more accurate, like the physical laws, and the data that you have is less accurate, the observation data, then you depend more on the physical solution. So like here, so when we were defining the physics total loss for the training, we were defining a separate term called lambda here, as you can see, this term. So this term can vary on the basis of the domain. So if we believe more on the physics of the problem, so this lambda will be higher. And if we are more confident with the data which we have, this will be much lower. Hope that I answered your question.
Yep. We can keep the conversation.
Yeah, surely we can discuss.
Yeah, no, but, yeah, thank you. Very good.
Some more questions? Yeah, please.
Thank you again. I was just wondering, going back to your like drag model, I was wondering, so you know the differential equation for the motion of the object. So why is it necessary to use a neural network to figure out the trajectory when you could just solve it analytically or computationally?
Yeah, to solve those equations analytically on such a high resolution, like 15 to 60 million cells, it is much more expensive than actually training a model, which has some upfront cost in training, but after that training cost, you will just infer from it. So it would be much cheaper. So
okay.
In that way, it is better.
Thank you.
Yeah.
More questions? Okay, let's greet Mehul again with applause.